All right, so in this video, we're going to show that if a function can be integrated on two intervals that are, like connected to each other, like right next to each other, then it can be integrated across the entire interval, and the integral on the whole interval splits it. It's the sum of the two integrals on the subintervals, basically. So this is actually a pretty, like, one of the easier theorems in this lecture, honestly. So this is the statement. So let f be a function on AB if A less than C less than B, and f is integrable on AC and CB, then f is integrable on AB, and the integral from A to B of f is the integral from A to C of f plus the integral from C to B of f. Okay? So the proof, again, is going to be basically by way of theorem 32.5. Again, right? So let epsilon be greater than 0. We want to show there exists a partition P of AB such that UFP minus LFP is less than epsilon, right? So all we have to work with is the fact that f is integrable on AC and CB, right? So the natural thing to do would be to try to pick partitions on those two intervals, right, and somehow add them together. And if you sort of work through that a little bit, basically it's pretty obvious that the upper sums on AC and CB will add together to form an upper sum on AB, right? And the same thing is true for the lower sums. So whatever the differences are between the upper and lower sums on the interval AC, and the difference and on the interval CB, the differences there will add up to be the total difference between the upper and lower sum on the entire interval AB. So we basically do another epsilon over 2 argument, right? So so there exists partitions P1 and P2, partitions of AC and CB respectively, such that the upper sum of F and P1 minus the lower sum of F and P1 is less than epsilon over 2, and the upper sum of F on P2 minus the lower sum of F on P2 is also less than epsilon over 2, right? And this is on CB, right? This is on AB, just to remind you, right? So then P, if you just take the points in the, oh, sorry, not AB, AC. If you just take the points in the partition P1 and the points in the partition P2 and just combine them together, you get a partition of AB, right? So if you take P1 union P2, then that partition, that is a partition of AB, and the upper sum of this partition equals the upper sum for the partition on P1 plus the upper sum for the partition on P2. And the lower sum is the same way. The lower sum for F on P1 plus the lower sum for F on P2, right? So, if you just kind of draw a simple diagram, let's say this is A or B, and then here's C, right? We have some rectangles. Something like that. Maybe that's the upper sum. Here's the lower sum. Like something like that. So, let's say, well, yeah. Right, the green area is the lower sum on AC, right? And then like the red area plus the green area, of course, is the upper sum on AC. And then let's say like, this blue area is the lower sum on CB. And then the, I don't know, the orange area is the upper sum. The orange plus the blue, I guess, would be the upper sum on CB, right? So this is lower sum. Well, this is, yeah, L of F P1. And then the green plus the red is the upper sum of F on P1, right? And then similarly, this is the lower sum of F of P2, and the blue plus the orange would be the upper sum of F on P2, right? So the lower sum, of course, is going to be the green plus the blue. And that's the lower sum of F for P, right? The overall P, the partition of AB. And then similarly, if you add together all four, that gives you the upper sum, right? So that's how, I mean, you can just see that they are, that they add together to give you the total lower and upper sums of F on the partition P of AB that we get, right? That's where these two equations come from. So then, from that, we can say that the upper sum of F for P, this is on the whole interval AB now, oops, minus the lower sum of FP is, this equals the upper sum FP1 minus the lower sum FP1 plus the upper sum FP2 minus the lower sum FP2, which is less than epsilon over 2 plus epsilon over 2, which is epsilon, right? So, so the integral from a to b of f exists, right? And then kind of like, as we've seen before, the integral from a to b of f is less than or equal to the upper sum of f on p, which equals the sum of these two upper sums, p1 plus the upper sum fp2, which is then less than lfp1 plus epsilon over 2 plus lfp2 plus epsilon over 2, which is less than or equal to the integral from a to c f plus the integral from c to b f plus epsilon, right? Because this lower sum is less than or equal to the integral from a to c, and this lower sum is less than or equal to the integral from c to b, and then I'm just combining these two epsilon over 2 terms, right? So, oops. And then similarly, the integral from a to b of f is greater than the integral from a to c of f plus the integral from c to b of f minus epsilon. So as we've seen before, this means since epsilon was arbitrary, right, the integral from a to b of f equals the integral from a to c of f plus the integral from c to b of f. Okay. Now, so technically, this shows that, like, if it's integrable on a, c, and c, b, that shows that it's integrable on a, b. But this can also this can go backwards, basically, because by what exercise we did in discussion, actually. So it was what, exercise 32.8. If f is integrable on a, b, then it is integrable on AC and CB for any A less than C less than B, any C between A and B. And then since that's true, then we can actually apply this theorem and conclude that the integral splits up this way again anyway, right? So we can go the other direction too, basically. Yeah. So you can always like either combine integrals when you have two intervals that like share an endpoint by adding them, or you can split one integral up into two integrals on two subintervals that share an endpoint too, right? Just as you're used to doing, right? We've just proved that now. Okay, so the last thing for this little bit is about piecewise continuous and piecewise monotonic functions. So a function f is piecewise monotonic on AB if there exists a partition P such that f is monotonic on each open tk minus 1 tk. F is piecewise, continuous on AB if there exists P such that F is uniformly continuous on each open tk minus 1 tk. So the reason we need uniform continuity is just that, you know, since we don't want to care about what's happening at the points tk, basically. So, but we also don't want to accidentally let f do some kind of like insane oscillation near one of these endpoints or something. So basically, they just use uniform continuity as a way to make sure that like f is actually well behaved on each of these intervals. It's just that it might not actually be like continuous right at the endpoints, basically, right? So let me just draw some examples of these types of functions real quick. Okay, so here on the left, you can see a piecewise monotonic function. One of the things I want to point out is you can see that like, you know, it doesn't have to be you know, all the monotonicity doesn't have to be like in the same direction on each interval, for one thing. Also, since they're totally like disconnected at the endpoints, like there's no relationship between these two, you know, intervals. It's possible that, you know, you could have like an increase. It could be increasing on one piece, and then suddenly on the next piece, it could be much smaller than somewhere over here, right? Like the value can jump back down at the endpoints or jump back up or whatever. So, and then the other thing is that like also piecewise monotonic functions can actually be unbounded. Like in this example, in the middle interval here, it's monotonically increasing and it's actually unbounded. And then also like they can have discontinuities in the middle of these intervals too. So like this piece, it's discontinuous at points in between T2 and B, but it's monotonic, which is what matters. So yeah, this is like a piecewise monotonic function. And then a piecewise continuous function, you know, as you can see, the pieces on each like open interval, they're uniformly continuous because they can actually be extended at the endpoints, right? You see how there's these open endpoints here? That indicates that like the limit exists as you approach each endpoint. So the function could be extended. So it's always uniformly continuous on each of these intervals, even though like the value at each of the endpoints of these intervals could be anything. It could be random. So it could be consistent. It could be like the limit, you know, the one-sided limit of one of these pieces of the function, or it could just be a totally different value. Like this one is just like a random value, right? So what's happening at the endpoints is just totally like up in the air, but on each, you know, open interval, it is uniformly continuous and it has well-defined limits as you approach the endpoints, okay? So that's a piecewise continuous function. So the theorem, there's a theorem here, which is if f is a bounded piecewise monotonic function, or f is piecewise continuous on AB, then f is integrable. Okay. And the gist of the proof is basically like, okay. So if f is bounded piecewise monotonic with partition P, right, where P is the partition so that it's monotonic on each like subinterval of P, then the restriction of F to each like open interval, TK minus 1 TK, can be extended to a monotonic function on TK minus 1 to TK, the closed interval, right? So since F itself restricted to the closed interval, differs. I'm gonna have to move to a new page. So F restricted to the closed interval differs from the monotonic extension of F restricted to the open interval only at the endpoints, if at all. Then the restriction, well, yeah, by a simple exercise, F is integrable on the closed interval TK minus 1 TK, and Yeah, well, yeah, for each k. So by the previous theorem, f is integrable on AB, right? By you know, n applications of the previous theorem, right? We can sort of stitch all of those integrals together to form the integral on the whole interval AB. And the argument for piecewise continuous is similar. Replace monotonic with continuous. Because basically, right, since piecewise continuous functions are uniformly continuous on each open interval, then if you look at the restriction to an open interval, if it's uniformly continuous, it can be extended to a continuous function on the closed interval, right? And then that continuous function on the closed interval, the extension of f restricted to the open interval, is only different from f restricted to the closed interval at most at the two endpoints, right? It could be the same, but it might be different at the two endpoints. But again, that doesn't actually affect whether the restriction of f to the closed interval is integrable or not. So that shows that f is integrable on each closed interval, and then you can do the same. So it's all the same logic, but just with continuous extensions instead of monotonic extensions. So yeah, anyway, that's yeah, that's I'm going to leave it at that for this video. So in the next one, we'll look at the intermediate value theorem for integrals, which you could also think of as kind of a mean value theorem in a sense. And then after that, we'll talk about some stuff from functional analysis, like the dominated convergence theorem and the monotone convergence theorem, which I won't prove, but I'll just discuss them. So yeah.